Hey everyone, my name is Ben Sims. I'm going to be talking to you about shaders, graphics, and optimization. This is something I'm working on with several people. It's a game known as Tech Hunter. It's still in development. So I'm a programmer at Foxie Games. I've been there for about a year and a half. I also work on Tech Hunter in my spare time. I've also worked at another studio in Adelaide called Odd Games. So these are just a few of the projects I've worked on or currently working on. First one is Tech Hunter, as I mentioned. This one is a game that Foxie Games released late last year. So I helped out quite a lot with that, doing environments, graphic shaders, some programming. So that one's called Dino Tamers, and that's available. This is Trucks Off-Road. It's another mobile game. It's got some pretty cool like mud physics and car physics and damage and all this cool stuff. And the last one is just a game that we're working on at Foxie Games, which is almost released. It's just going through some final stages. It's a pretty cool like sort of open world multiplayer game. Lots of nice natural environments and that sort of thing. So you probably all have some idea in your head of what graphics are. Specifically for development, there's a few areas you might want to keep in mind. So to start with, you have a lot of geometry in your scenes, which, there's characters, buildings, terrain, foliage, vehicles, items the player might use, like a armor or weapons or a key for a puzzle game. So all that is made up and supplied with 3D models, which are made by artists, or you might get them online or generate them procedurally even. And then you use materials to give all these models their appearance. So it defines the color, certain attributes like whether the material is reflective, metallic, fine details like little bumps on the surface that can be represented with special textures, normal maps, which some of you guys might know what they are. So you've got materials and you've got geometry. Next thing is usually lighting. So without lighting, everything doesn't look very interesting. In an outdoor environment, you'll usually have a sun. You may have a few point lights as well. In indoor environments in games, there's usually a lot more individual small light sources. You might have specialized lights, such as spotlights, if the player has a torch, or if you're driving a vehicle and it's got headlights. And there's a few other special cases. If you've got some fire, you might also just have a nice circular light lighting up the area. Or if your game has magic and spells, you might want to light up the area around where the player is using their magic. And then outdoor games, usually the sky is a light source as well. So if it's a game with a dynamic time of day, you'll change the ambient lighting depending on the color of the sky. So that usually provides a lot of realism and immersion. Then you've just got other effects which also contribute a lot to the graphic style of a game. Smoke, fog, water, a few other effects such as weather effects like dust, rain, clouds, snow. And finally, a lot of games have quite a bit of post-processing in them nowadays, especially on modern PC and console. So usually this just does like color enhancements, lighting enhancements, some other effects like motion blur, depth of field. They just kind of can enhance the gameplay feeling. They can also be used to highlight certain visual elements. So they can help not only with the visuals, but also with the gameplay mechanics, if you want the player to focus on certain things. So just in case anyone's still a bit unsure about graphics, just a few modern games showing off just some of those techniques I talked about. You can probably see a little bit of most of those techniques in each screenshot. So, has everyone here heard of a shader before? Yeah, most of you? Cool. It's probably a term you might hear occasionally. You might not have a concrete idea of what they do. On a fairly straightforward level, they basically just take geometry, like this, and they transform it into pixels on your screen. And they also apply lighting and shading, and you end up with something like this. So there are many different techniques you can use in your shaders to accomplish these kind of effects. Lighting and shadows, that's fairly important and fairly common. There's also certain texture-based effects. So you have a color texture to describe the general appearance of your object, but you may have additional textures which provide more data, such as normal maps, which provide extra surface detail. Specular maps, they control how shiny or reflective an object is. Parallax maps is another technique. It sort of fakes extra depth in the object. So if you're rendering something like terrain, generally you want to blend quite a few different textures. For example, grass, dirt, sand, snow, and rock. So usually you'll have a specialized shader which is capable of blending all these different artist-painted textures onto a single model. And you have certain special effects which might not be used on every surface in a game, but it's used on specific materials. Translucent items like candles, human skin, water might use that kind of shading. Metallic surfaces also have a few extra visual elements that make them quite unique. Reflective surfaces. These days most surfaces have some degree of reflectivity. If it's really reflective, like a really shiny floor or a mirror, there might be some extra special shader code going on just to give them their mirror-like appearance. Yeah, and then you have some even more specialized effects, like a water shader is probably going to be unlike any of the other shaders you write, just because it's got so many important and complicated visual elements. You can also do something like animated foliage. So if you've got a huge thick forest, it's not really practical to animate all of your trees in the same way that you might animate a character. So in a shader, you can apply simple modifications to the position of an object. So you can simulate leaves, wind bending. You can even simulate grass moving as the player walks through it with a few more techniques. As I mentioned, terrain as well usually has a few special cases to handle just because it's very big, detailed, natural, and has a lot of texture detail. And one more example, dynamic sky and clouds. So for a while, a lot of games might have just used a simple cube map texture or just a scrolling layer of clouds or something. A lot of games nowadays are starting to use these sort of fully dynamic real-time systems, which means you can have a large amount of variety. You can have just different times of day, different weather conditions, and you can even have it influenced by player actions or events that are in the game. So in addition to the obvious uses, coloring things that you might see directly in the game, you can also use shaders for some other things which might not be as obvious. For example, player customization. You might want to let the player choose like their skin color, their hair color, the color of some highlights on their clothing. It's a bit difficult to sort of make hundreds of variants of the same textures just to handle all these little color variations. So you can use a shader to tint certain parts of a model while the game is running, and that allows the player to just sort of have more control over their appearance. And you can also use it for things like tattoos, scars, or symbols on your character. Or if you have like a vehicle or something in a game, you might be able to place dynamic logos and stickers and patterns. So those things can really sort of improve the player experience, give them more customization, and it can also take a bit of strain off of your artwork pipeline because you don't have to get so many different art assets made. You can sort of get a lot more out of what you've already got. And even special effects like armor and equipment getting damaged or rusted over time. So the actual physical appearance of the object will change. And then if it's a game like Skyrim where you can, you can't repair items in Skyrim, the one before Oblivion. If your sword's really rusted and then you repair it, its appearance goes back to like shiny and brand new again. There's also some subtle visual effects you can do. Again, these are things that can sort of help with getting more out of the content that you currently have. You might not have the budget to make hundreds of tree models, and even if you did, it might not be the most performant solution for your game. But you might be able to reuse a small amount of tree models just by doing subtle variations in a shader, such as just tinting the hue slightly giving some trees a bit more yellow or orange than others. You could also do this depending on the location in the world. If you had different biomes and they had different sort of colors and moods to them, you could actually use the same object in lots of different biomes and it would still look like it fits in to the world. And if you have a lot of really cool weather effects in your game, you might want the world to get covered in snow at one point, and then you might want it to go back to not being covered in snow without having to double up on the amount of assets. So you can use shaders to overlay a snow texture, change the way the shading and the reflectivity happens. Shaders can also be used to improve performance in certain situations. So you can take screenshots of an object and save them into a texture. This technique is known as billboarding. So using a special type of shader, you can figure out the angle the player is looking at an object and show the appropriate texture. So at a distance, this can give you quite a lot more performance with certain objects, and the player may not even notice that it's not the model. Certain natural effects, like ocean waves and caustics, for example, these can be quite expensive to simulate in real time, especially if you're targeting perhaps like older mobile devices. You probably don't want to be doing caustics calculations every frame. But if you have a way of calculating, say, a 2-second loop, you can save that into a sequence of textures, and then in your shader, all you need to do is just use that one texture and then change it every few frames, and it's going to look pretty much exactly the same, but it's going to run a lot faster. Atmospheric scattering is sort of a technique to render the sky in a realistic way. Again, it can be a bit complicated and slow on some devices, so shaders provide a way to calculate and save all that data into a texture, and then reuse that data at runtime. And you can also use shaders on modern hardware for non-visual information. For example, you can use it to generate terrain procedurally. You can also use it to do complicated ocean simulations. Even though the player may only see a small amount of the ocean at one time, you can be calculating a much larger simulation. So at this point, you might be wondering, can't you just get everything from the asset store and not have to write any shader code yourself? Possibly. So asset store is great for learning and prototyping. If it's something you've never written before, it's probably going to be faster than making it from scratch. You've got community support, developer support, though that can depend on the developer. However, they do have some downsides, depending on what you get and what you want to use it for. They're usually quite general, so an asset store plugin can't be optimized for every single use case, and depending on what you're using something for in your game, you may not need a lot of the features, and it might be always doing these certain calculations anyway, even though you don't need them. So with a little bit of custom knowledge, you may be able to create something yourself or tailor an existing solution to be a lot more optimized for your specific use case. I've seen a lot of assets that say mobile ready, and it's kind of like there's no like criteria for that. They might have just put it on the latest mobile phone and been like, yep, it didn't crash, it's mobile ready. So I'd always be a bit wary when something says it's mobile ready, especially if you're targeting older mobiles. There's a lot of stuff that just won't run, or so slow that it's not worth it. So you don't want to be finding out after you spent several months with shader language. So everything inside here is actually non-Unity specific shader code. So all the online resources you might find about general shaders not related to Unity are valid here. So to get some data into the shader, we just have to define some properties. I won't describe these too much because they're fairly straightforward. There's only a few you need to learn.
Ben, do you want to zoom in a little bit to the screen?
This one?
Yeah, just zoom in a bit through if you come
Oh, yeah, I get what I mean. Fuck, how do I do that without a scroll? There we go. That better? Yep. All right, cool. So we're going to use a color, which the user can control, and a texture. So we basically define some inputs the user can give to the shader. And then within the actual shader code, we just have to tell the shader that they exist. It's just a bit of a way of communicating between Unity's magic shader stuff and the actual proper shader implementation. It basically saves you from having to do a lot of C++ bindings and things like that. So we just have to tell the shader what data we want from the program, and then the program will give it to us. It always has to give us a vertex because we always need to output a position on the screen. Everything else is optional. We're going to grab a UV coordinate. If you don't know what that is, it is basically a 3D model unwrapped onto a 2D texture, I guess, a 2D space. And it's used to apply textures to the model. So we just need to get that information. So a shader is broken up into two main parts. There's the vertex shader. So that is this function here. So that is the part of the shader that tells us where the vertex is on the screen. And then there is the fragment shader, or the pixel shader. It's often called that as well. So to get information in the pixel shader, like a UV coordinate, we first need to pass it from the vertex shader to the pixel. In this case, it's quite simple. We just set the output UV coordinate to the input UV coordinate. And now in our fragment shader, we can use a built-in function to get this texture data. So shaders have a bunch of built-in functions that take a lot of hard work out for you. Like there's trigonometry, there's various math functions, a lot of texture-specific things, and it's all available online. If you just look up HLSL documentation, you'll find everything you can use. Ties back slightly to when I said not all assets are suitable for all platforms. There's different versions of shader languages. Older devices may not support the latest features. So a lot of general stuff you do, like just textures, colors, a bit of math is fine. There's some more complicated things which you probably won't find yourself using, but if you are concerned about cross-platform compatibility, it's just worth double checking. Okay, so I'm just going to get the texture data using a built-in function called text2d. It's a 2D texture. So I just have to give it my texture name and my UV coordinate. Now I also created a color variable at the top because I want to give the users a color as well as a texture. So we're going to tint the texture color by the color, which is really simple. If you multiply one color by another, it's just going to tint it. Oh, and I need to give this variable a name. Alrighty. There. So this is going to hopefully sample the texture, tint it by a color, and give us the result. Great. So we didn't actually assign a texture to the model because we couldn't, because we didn't have a texture slot before, but now we do. And we also have a color. So even without a texture, I can still change the color because the default value for that texture is white. All right, so cool, we've got textures. And we can tint that texture. There we go. So it's probably not useful for this kind of model. Keep in mind things like this color, you can modify it from code at runtime. So if you want to highlight an object, you might want to pulse the color to indicate it to the user. Just going to create a couple more textures just to show off a bit of variety. Just bear with me. So there's an important distinction between shaders and materials. A material is kind of like, it's linked to a shader. So you have one shader, but you might have many materials that use it. And then each one of those materials may use many textures, different colors, etc. Sorry. Forgot to name my textures. It's alright. Most projects I work on, the textures aren't named anyway, just because there's much more important things to do. So I'm just dragging these materials onto these planes that I've created, just so I can show you that we can get a few different, a bit of variety out of our one shader. Cool. So we've got one shader, but we've got 5 different materials. So it's quite simple. We have a light in the scene. However, if I rotate this light, apart from the sky, nothing is actually happening. So let's quickly do something about that. So I just have to add one little bit of Unity-specific magic. So Unity uses this thing called tags to communicate certain extra information. In this case, we're just telling Unity that this shader needs lighting information. With shaders, you can also include extra shading files, which I think that's it. So Unity provides a bunch of shader files which have a whole lot of helper functions. They deal with like how Unity handles lighting, shadows, cross-platform compatibility as well. They've got a lot of their own code to handle how different devices might do things like light mapping or fog. So if you learn about these things, it's good to try and use the built-in functions where possible, just to avoid any cross-platform differences. All right, so we just need one more piece of information to light our objects. So it's called a normal. And the way lighting is going to work in this situation, if the surface is facing the light, it's going to be fully lit. If it's facing perpendicular or away from the light, it's not going to be lit at all. So a normal is just generated by a modeling program usually, and it will just tell us if part of the surface is facing a certain direction. So we're going to do all our lighting in the pixel shader. So once again, we just need to pass through a bit more information. Now I'm going to use just one other built-in Unity function. This is going to allow our lighting to work correctly with different rotations and scales. A lot of built-in Unity functions, you just kind of learn when to use them. You don't have to worry too much about what they do. If you are curious, you can always find out more information. A lot of online tutorials will also cover most of this stuff. Cool. So all we're going to do is we're going to use a mathematical function to figure out if the normal and the light source are facing the same direction or not. There's a pretty convenient function called a dot product, and it's built into a shader. So Unity provides the light direction in this astutely named variable. So if we do this, this will tell us whether the light is facing the surface or not. And then we also want to tint that by the color of the light. And finally, if the surfaces are more than 90 degrees away from each other, the result will actually be negative, which will actually have some weird visual effects. So we're just going to clamp the result so it never goes below 0. And finally, we can tint the color by the lighting just by multiplying it. And we want to make sure we're only modifying the RGB channels, not the alpha channel, even though we're not using it. Yeah, quite subtle, but we've now got some lighting. And if we change the color of the light, it will also change the color of the object. So one little thing you might notice is the bits that aren't facing the light are very dark. They are pitch black. So there's one extra little trick that is used in games to prevent that from happening, because in the real world, even though light may not hit a surface directly, usually it will hit something near the object and it will bounce in different directions and illuminate objects even though they're not facing the light. So in games, this is called ambient lighting. We're just going to use a magical Unity function to handle that for us. So Unity's ambient lighting is directional, even though a lot of the time you might just have a single color. Because you have like nice dynamic skyboxes, you might not want every direction to give you the same light. You might want the ground to be a bit more dim. So this function is just going to handle it for us. We're just going to give it the normal again. So if we just add the direct light and the indirect light together before multiplying it with the existing color, we've now got some ambient lighting. So you can see there's the direct lighting, and from behind we've got ambient lighting. So in Unity, because the ambient lighting is calculated from the skybox, if we rotate the sun and I set the lighting to auto-generate, it's actually going to affect the environment in a nice realistic way. You can actually update this at runtime. So you can actually have a very nice natural sort of time of day system. Cool. All right, so that's a pretty basic example of how you can do just some simple lighting, textures, and colors. There's a couple more techniques I could show you. Does anyone want to see how normal maps work quickly? Raise your hand if you're interested. Yeah, cool. All right, I'll do it quickly. It's a bit more complicated, so I won't tell you everything I'm doing in detail. We're going to use one more texture called a normal map. Just giving it a default value so that it looks somewhat correct even if you don't have a texture assigned. So one of the frustrating things about shaders in Unity is you have no IntelliSense, which means the only way to find out if you made a mistake is to wait for it to compile, and your entire game mode goes a nice bright pink color. But thankfully the compiling is really short, so it's easy to just go back and fix your mistakes. So there's just one piece of data called a tangent. It's kind of like a normal. It's generated automatically by modeling programs usually. You don't really have to worry about it. You just need it for normal mapping. Once again, I'm just going to pass it from my vertex to my fragment shader. Sorry, we're already about halfway there. Hopefully that works. So, important thing, I'm going to do my normal mapping before my lighting, because normal mapping will actually affect the lighting. That's what gives it its effect. So normal maps are packed in a specific way for certain platforms, which means you can't just use them like a regular texture. You have to use a bit of extra code to make sure they work properly. Unity provides a built-in function. So once again, you just learn when to use it, and then just use it unless you have a good reason not to. So that's my normal map. Now I have to calculate one more piece of information. If anyone knows much about shaders or math, you might know what I'm doing. Almost done. Just a bit of Unity specific magic again. Oh, just gonna change one thing. I'll be slightly surprised if I haven't made any errors so far, but we'll see. Okay. So basically what this has done, this has sampled the normal map, and it has then replaced the normal from the vertexes of the model with the normal map. So hopefully this is going to give us a lot more detail. And I've just told my calculations to use the normal map instead of the vertex normal. Now we're probably going to see some of that nice pink texture I was talking about. Maybe not. Cool. So we haven't actually assigned normal maps yet. That's why nothing happened. But that's okay. Just going to zoom in on this texture, and hopefully when I assign a normal map, you'll be able to see the difference. Yeah, did something. So normal maps, they're very dependent on the surface that they're on. Some normal maps might not be adding much. So if you are going to use normal maps, you want to make the most of them. So that texture there is probably a good example. You can see, yeah, you can see how much depth that's added. It looks, quite three-dimensional now compared to.
That's still just a flat image though.
Yeah, exactly. So it's just a flat model, but the texture provides extra information on how it can respond to light. So this is a much cheaper technique than if you were to model all of those rocks using vertices and triangles.
How does it know where to put the shadows in as a 2D image?
So they're not exactly shadows, it's just our lighting is coming from...
Does that move with the sun as well?
Yes, it does. I think my normals might be coming from the wrong direction. But
Yeah, but the idea is that.
Yeah, exactly. So let's just pretend the lighting is coming from that way instead of that way.
Perfect.
Yeah. So yeah, you can see how that adds quite a bit of detail. And they're also quite artist-friendly as well. You can use a program like Substance to just paint a lot of extra detail, and it just gets baked to a normal map. It's a lot quicker than having to model a whole lot of extra detail by hand. Yeah, you can see all these little panels and stuff. They now have a lot more definition. Cool. All right, I might just leave it there. I was going to show you specular mapping as well, but that'll probably take a little bit longer, and I'm not sure how tired everyone is. So we can see that we didn't actually need to write too much code. It'll probably take you a few tries to get this sort of stuff working in the first place. It's probably a lot quicker to just use like a shader graph tool or something like that just to connect some nodes. But this actually gives you some more insight into how things are actually working under the hood. And if you are targeting quite performance-intensive applications like older mobiles or even modern platforms, and you really want full control over your performance and your shader capabilities, you might find yourself wanting to write code in this sort of style occasionally. Cool. All right, I'm just going to finish up with just a little bit of information about optimizations. I'm not going to get too technical with this stuff. It's just some general things to keep in mind. So always keep your target platform in mind. That probably goes without saying, but you don't want to, have physically based rendering and several lights with dynamic shadows if you're targeting, mobile devices that are older than a couple of years, because you probably make half of your game, get your visual style set, and then test it on an older phone and realize you need to rethink most of your artwork and levels. Modern PCs and consoles are quite powerful. It's still easy to get carried away though. Post-processing, too many lights, huge shadow resolutions, huge textures, millions and millions of triangles. Maybe a few million is okay, but you just have to make them worth it. Some fairly common knowledge is still true today as it was 10, 20 years ago. Vert tricounts, you want to keep those to a sensible level depending on your device. Draw calls, it's basically a function used to render a mesh. They're quite expensive, so there's optimization strategies for reducing that, but if you're concerned about performance, you want to start learning what they are and what's appropriate for your target device and how you can keep them to a minimum. Memory usage as well. Pretty much as long as you're under your memory budget, you'll probably be okay. But if you do hit that budget, then it gets really hard to remove things, especially if you're late in development. So if you just keep this in mind the whole time, it may save you some headaches. And it's always important to profile on your target devices. You shouldn't really just make assumptions about what might be slowing your game down. You want to get some actual data, and you want to optimize the things that are the slowest. And you don't want to waste too much time optimizing tiny little things which may not be having any significant effect. And when you do profile, average frame rate is important, because obviously games aren't very fun at like 10 frames per second. But even if it is 40, 50 frames per second, if you've got a couple of frames in there that are taking a couple of hundred milliseconds, then it's going to feel very stuttery and bad. So you want to focus on spikes as well as just averages. And as I mentioned, just optimize the stuff that's actually causing noticeable slowdowns. Try not to focus on things that aren't as important. So there's two main parts of hardware. There's the CPU and the GPU. You want to make sure they're both you want to make sure they're not slowing each other down, basically, because a lot of situations you may have one waiting on the other. So you just want to make sure you're targeting both with your optimizations. So if you've got a really big game world with lots and lots of objects, the CPU has to determine what is visible to the camera. Because everything that gets sent to the graphics card has to be processed to some degree. So if you figure out what's entirely not visible, you can save a lot of work. Game engines do this for you, but there is a slight cost to it as well. So it's good to do what you can to keep that cost low. So having not a crazy amount of individual objects. If you've got like a pile of boxes, for example, you might just want to combine them into a single object. If you've got a really big game world, which is just a single scene, you might want to break it up into individual scenes and load them in and unload them as the player moves around. This is quite difficult, so think about these kind of things before you make something like a big open world game. So as I mentioned, draw calls can be a performance issue as well. It's good to get familiar with what they are. If you use the same materials, the same shaders across objects, it will help a lot with that sort of thing. There's a few techniques to reduce the amount of draw calls. You can render the exact same mesh multiple times with a single draw call using a technique called instancing. So rather than making 100 different tree models, you might want to just make 10 and try to use other techniques to get some variation, like scale, rotation, that hue variation technique that I talked about. And having lots of lights, lots of shadow casting objects, that can all increase it as well. So these are things that you might want to think about early on because they can affect the visual style and your level design. So they can be quite time consuming if you do need to go back and modify them. And with memory, it's not too hard to stay under the limit. Just don't use like more mesh or texture data than you need. Keep your resolutions sensible. Don't just import everything at 4K. You can compress meshes and textures as well. This saves a lot of space, and a lot of the time the visual quality difference isn't really noticeable. And if you are targeting something like mobile, a little bit of visual quality reduction is something that players will probably just have to accept because it is a mobile device, and the screen is also quite small, so they may not notice. And finally, the GPU. So you want to make sure your CPU is fairly optimized before you start modifying your GPU, optimizing for your GPU, because if the CPU is really burdened with a lot of stuff to do, the GPU is just going to be chilling and doing nothing. So complicated shaders, quite obviously, they have to do a lot more work, so they're going to take longer. This usually just ties down to picking what's appropriate for your platform. For mobile devices, it may be better to pick a non-physically based shader and not use heaps of reflections, normal maps, that sort of thing. Just save them for what really needs it. That can affect your art style a lot, so it's good to think about that early in development once again. If you are writing your own shaders, some functions are a bit more expensive or a lot more expensive. In general, most stuff you'll write when starting out is probably going to be pretty fast. You don't have to worry that much. When you do get into some complicated techniques, if you're doing like anything with like volumetric data or 2D textures which contain like height fields or something, and you want to do some crazy parallax mapping, those are the sort of specialized effects where you do have to be a bit more concerned about performance. So when you have a detailed scene rendering, you might have a lot of objects that are sort of in front or behind each other. There's a good chance a lot of those will render more than one. There's a good chance a lot of those objects will get rendered but you might only see a few pixels from the object that's in front. So this is called overdraw, and it can be quite slow on mobile devices, and even PC and console, especially with like 4K resolution. It's definitely something you still need to think about. So again, using like LODs and not having too much data to render at once can help, and just how you design your levels and your visual style. Particle effects as well. If you've got a really dense particle system, like hundreds and hundreds of like smoke clouds like in a tiny space, you might have noticed that really slows down everything. And again, that's because all of the pixels behind those particles are all getting like rendered heaps and heaps of times every frame. So it's still something you want to be careful of, especially if those particles become really big on the screen and they're covering the whole screen. So memory bandwidth is basically all the data that the GPU is using, like your meshes, your textures, lighting information, matrices, blah, blah, blah. This is all going to be transferred really fast on the GPU, so it can be used for all the calculations. If you start running out of memory bandwidth, everything just kind of gets really slow. So if you stick to some general guidelines, most of the time you'll probably be okay. Keep your texture resolutions not too high. Use compressed texture formats, because these actually use a lot less memory bandwidth. Some shader techniques that use a lot of texture lookups can be expensive, so just be careful of that. And then things like post-processing, shadow mapping with really high resolutions. These are all things that can slow down games quite a lot. That's why even with like modern computers, you don't really see games having like 16K shadow maps and 8K textures everywhere. Usually they try to keep it reasonable. And the last thing, just vertex processing. So every vertex sent to the GPU needs to be processed to some degree, even if it's not visible. So for modern PC and console, this is probably several million per frame. So you don't want to be processing more than you really need. So, making sure your culling systems are working properly, designing your models to not have crazy vertex counts, just general sort of good practice things for modeling and texturing can really help quite a lot, and it saves you having to then do a lot of extra work later in development. Cool. All right. Just a few resources. I think this will be available online anyway. The first two websites, first one especially, takes you through pretty much all of Unity's shader-specific features and some advanced techniques. And they write all of it from scratch, and they're quite good at explaining why a lot of it is done. So I definitely recommend that one if you want to start writing shaders from scratch. The second one, sort of similar. It's a bit less focused, a bit more general purpose. Like there's just an article for this technique, an article for this technique. They're both pretty good. You probably find yourself going through them a bit. The next three, they're just good places to just find out about, how a lot of graphics effects are done in games, certain techniques, how you can implement them. A lot of the time, it's not just going to be shaders. It's also going to be talking about, how you can do stuff from the CPU side, what mesh data you need to generate, that sort of thing. If you're interested in a bit more about how graphics hardware works internally and what gives it its amazing speed as well as its severe limitations, the next two are interesting. And then